Okay, let's start. Good day, everyone. This is C.Jia from Peking University and Pengcheng Laboratory. This talk is about a project in MPI named End-to-End Video Coding, EEV. So in this slide, we summarizes what we are designed to do and what we have achieved in the past several months, so that we will see that the neural network-based or AI-based video coding technology will be a future direction for the video community. So in MPI, we usually research or standardize the AI-based technology. So in EEV, we focus on video coding schemes using fully neural networks. So we summarize recent progress on learning-based video compression in twofold. The first part is the frame generation-based end-to-end video coding. So that is to say, we can interpret such frameworks as a neural intra codec plus frame interpolation. So representatives can be observed by some top conference venue in the past several years, so that researchers have investigated many powerful models that can be used for frame generation with some residual compression to realize video coding. The other part of this scheme is the called hybrid framework with end-to-end video coding. So this framework mimics the conventional prediction plus transform-based codec, but the difference is that the entire framework is realized by neural networks, and such framework could be optimized using the end-to-end fashion, so that the overall compression efficiency could be realized. So the very beginning work can be observed is in 2017. So it has been 5 or 6 years from the starting point. And we are observing that increasing attention are received from both academic society and industry, as well as the standardization groups, that a lot of attention has been paid to the related area. So in MPI EEV, we realize particular milestones, and in November of 2021, we officially kicked off this project. And the working mechanism within this group is that we hold a bi-weekly meeting, and we have another general assembly meeting at the end of each month to report the progress. So as time goes by, we have spent over a total year plus another 4 months. So we have really made several milestones. For example, we made 4 major versions of a reference model, and the performance is increasingly by incorporating more and more neural network-based coding tool. And we also contributed the working draft of SOTA solutions in end-to-end coding at the beginning stage of this project. Another interesting thing for this group is that we are currently focusing on the drone video compression, because the unmanned aerial vehicles have captured the video have different content characteristics with that of natural video contents, so that we find out that the learning-based codec might benefit the coding efficiency for those videos. And to give a quick overview of the AI-based end-to-end video coding, and which is the starting point of the EEV reference model. The label is the EEV 0.1, that is the open DVC, which is donated by our friend from ETH University. And this entire framework is realized by neural motion estimation to calculate the optical flow, the pixel-wise optical flow, followed by the neural motion compensation to get the prediction frame. Therefore, the interpredictive coding can be realized. And once you got the prediction frame, you can got the residual codec, and using the learning-based image codec to compress the residual information. Therefore, the entire network can be realized by a neural network, and they can be trained by designing the rate distortion learning objective. And the essential part for the bitrate estimation are twofold. One for the motion field bitrate estimation. The other one is the residual coding network. But luckily, we have borrowed some knowledge from learning-based image compression, so all of those problems could be resolved, and the entire network can be trained end-to-end. So at the beginning of this project, we find out that the OpenDVC or EEV 0.1 have a similar performance against the open source implementation by FFmpeg X264 and X265. So that this is a solid baseline for this research group. And we start to add novel coding tools on the top of the OpenDVC module. So as I have mentioned, we in EEV group targets at the drone video coding. So to realize the drone video coding, we need to establish a benchmark that is composed of drone videos. So by to realize this objective, we collect public benchmark and release the representative data set that has different types of content. For example, you have different light condition for daytime and nighttime, and you have different viewpoint and have different angles, so that the scales or the size of the object within that sequence are different. And we also have different types of lens distortions. For example, in this column of test sequences, we are using the indoor drones capture the videos, because as you can observe, there is some fish eye distortion, and the imaging characteristics are totally different from that of the natural content, so that it is interesting to investigate whether those videos could be easily compressed, and how far can the learned video codec go for those videos. So all these benchmarks are publicly available upon request, and you can visit the EEV website for further information. So here, this picture or this slide gives the overview summarization of those drone video benchmark. So the largest video resolution is over 2K, while the smallest resolution is 640 × 352, and each of the clip has 100 frames with standard dynamic range. So the major difference between them are the content characteristics, and the scene features include the outdoor scenes and indoor scenes. So regarding the EEV model development, after the starting point, we have integrated several novel coding tools. For example, we added the motion compensation prediction enhancement on the top of EEV 0.1, so that our performance could be enhanced. Subsequently, we add another two novel tools named scalable residue codec and the in-loop filtering neural network into the framework, so that the framework is further enhanced, and the ray distortion efficiency is much better than that of the previous framework. And for EEV 0.4, which is a major change in terms of the model design, because we have discovered that the motion representation or motion coding efficiency in the previous EEV reference model has not efficient enough. So we propose something like motion decomposition approach to decompose the motion vectors or the optical flows into two parts. The first part is the intrinsic motion, and the second part, we call it compensatory motion. So the intrinsic motion does not need any side information to for computation. It is directly learned from the decoded picture buffer, and which means that we only need the reference pictures to generate such motion information. And if you only use the intrinsic motion, your prediction efficiency is not good enough. Therefore, to realize further information enhancement, we one thing come to our mind is that we can send the side information which contains the original information in the from the encoder, so that we call it compensatory motion. We concatenate the original image and the reference image together, and to learn the motion between the pre-stamp images with respect to the reference picture, and we signal that information by using variational-based autoencoder. Therefore, at the decoder end, we can easily restore those compensatory motion information. Another interesting thing we find out is that if we directly use motion prediction within the pixel domain, as we have down in the EV 0.1, 0.2, and 0.3, the efficiency is limited. So in the EV 0.4, we finally realized that we can achieve the interprediction within the deep feature space domain, so that both of the intrinsic motion and compensatory motion prediction or compensation are achieved using the residual STM module, and followed by a feature restoration network to convert those deep feature back to the pixel space. Therefore, we can apply our previous investigated modules, such as the motion compensation prediction refinement, as well as the in-loop filtering network, and both of them has been investigated in previous EEV models. Therefore, the entire network is optimized, and we can realize higher coding performance, which is better than any of any version of our previous EEV models. So to compare the performance, we list the EEV 0.3 and EEV 0.4 here, and we compare our method with the HEVC reference software with screen content extension. And the test condition is defined in this slide. We're using the low delay P configuration with the input bit depth of 8. Because all of the processing color space is RGB, so we use the screen content extension. And another important setting is that we set the entry period to be 16 to align the test sequence. To align the test condition with MPI EVC. By doing so, we can easily compare the learned codec and the conventional codec. So in the left panel, as you can see that the EEV has around 20% of bit rate reduction with respect to OpenDVC, which is the starting point of this group. And on average, the EEV 0.3 has inferior performance with respect to HEVC because the indoor scenes in Class C are significantly worse, while the remaining 3 classes of test sequences are clearly better. So on average, the EEV has worse performance than HEVC, and the right panel indicates the rate distortion curves for the 3 codecs: the HEVC, the EEV, and the OpenDVC. But for EEV 0.4, we got a very powerful performance, as you can see, both from the table and the curves. We are better than H.266 VVC, and the VTM software is used, and we can observe that using the MSSSIM based metric, the EEV 0.4 is better. And for the right panel, this table indicates the drone videos, and of course, we are still better. So here, this slide depicts the visual quality. As you can see, the EEV model has significantly better reconstruction quality against the VVC software, and it restores the textures and has better subjective quality. So for future use case, we are going to support the compression domain analysis without retraining and decoding, since this is the advantage of learning-based codec. And we are also analyzing the complexity and the operation cost for the learning-based codec to compare it with the conventional one. So that is the introduction of the MPI EEV project. Thank you. So that is the presentation of this group. Thank you.